Hi friends, welcome back to my channel, and today we are going to see three really exciting problems which will drive home a lot of basic concepts in mechanical engineering. All these three questions were asked in GATE 2020, and all the three were 1 mark questions. Without much ado, let's get started with the first question. So, in this problem, we have a helical gear with 20-degree pressure angle and 30-degree helix angle mounted at the mid span of a shaft that is supported between two bearing at the ends. Now, they are asking as the nature of stresses induced in the shaft. One additional piece of information, see, this kind of questions will be asked in interview. I had an experience where one of the interviewee asked me this question: can you tell me what is the kind of stresses that will be induced in a shaft when you have a gearing like this or a gear system like this mounted onto the shaft? In order to answer this question, we should go to the free body diagram of a helical gearing. So I have here one of the free body diagram. As you can see over here, there are predominantly three forces acting at the gear tooth. One is the tangential force, the most predominant one, because that is what causes the shaft to rotate, or that is the component from which majority of the power transfer will take place. But at the same time, there are other two components as well. You have a radial component, that is because your pressure angle, and then you have an axial component, that is because of your helix angle. Okay, so just to drive home a little bit more clarity regarding the forces, different forces that are acting on a gear tooth. So here you can see this is the tangential force which gives you the power, which contributes to the power transfer. This is the net, or the net force acting at the section, now at this gear tooth. Then we have three components of this force. One is the radial component, then we have this axial component, then we have this tangential component. So we have a separate formula for also to compute all these radial and tangential and then axial component. Here our phi n is the pressure angle, this phi n is the pressure angle, and this is the helix angle. So you can see there won't be any axial component of the load if psi is 0. But here in this case, we have a non-zero helix angle and we have non-zero pressure angle, which in turn tells us, that we will have all these three components. But the question is, they are not asking us to compute these forces and all. They are asking us what will be the kind of loading. To explain that, I think this is the best figure. I'll zoom in a little bit. So first thing is, WR will cause a bending of the shaft because it is just a lateral load for the shaft. Similarly, WT will also cause a bending because see, this is pretty straightforward that WR is a lateral load to this shaft. Similarly, this WT, I can transfer to here WT with a corresponding torque or a moment. So that means WT will cause bending in another plane. So if you, let's say this is my x direction, then this is my y direction, and then let's say the perpendicular one is z, then WR will cause a bending in the XZ plane, while WT will cause a bending in the XY plane. Make sense? Similarly, this WA component will cause an axial stress on the shaft. So, bending in two planes, then there is an axial stress on the shaft due to this WA, which is pretty straightforward. But we are not done. Why we are not done? Because this WT will cause a torque about the shaft, which will in turn cause some shear stress in the shaft again. So I am not going into the formula of all these stresses, but tell you that this WT will cause a torque, WR will cause bending, WR will cause bending in the XZ plane, WT will cause bending in the XY plane, then WA will cause the axial stress. A beautiful example or a question, I would say. Now let's go ahead and pick one of the results. I think the correct answer is this normal stress due to bending in two planes and axial loading. So normal stress is because of the bending as well as due to the axial loading, WA. WA is arising only because of the non-zero helix angle. We have a 30-degree helix angle in this problem. And shear stress due to torsion. So this is the correct option. This option, let me highlight it. So this is the right answer. Normal stress due to bending in two planes and axial loading, and then shear stress due to torsion. Hi friends, so now we will go ahead and solve another very beautiful problem, I would say, from engineering mechanics. This was again asked in GATE 2020. This was a one more question. So the question goes like this: an attempt is made to pull a roller of weight W over a step. The step is shown over here by applying a horizontal force as shown here in this figure. Keep in mind that this horizontal force, capital F, is actually passing through the center. Okay, just be very careful about that fact. Then they are saying the coefficient of static friction between the roller and the ground. So you have ground over here and here as well. They are very explicitly telling you this coefficient of friction is there between the roller and the ground as well as at the edge of the step. I love this detail because this is one particular characteristic of GATE questions. They give you all the details. They never leave any space for guesses, or their questions are framed in a really nice manner. So they give you the coefficient of friction throughout this surface, throughout this bottom surface over which our roller is rolling. Then they are asking us to compute or to find the correct free body diagram of the roller when the roller is just about to climb over the step. A very simple problem at the first sight, because here they have given us four different free body diagrams, A, B, C, D. We just need to pick one among the four. And one thing, what happens when it is just about to climb over the step? When it is just about to climb over the step, the contact at this point no longer exists. That means there won't be any external forces acting on the roller from this point. Make sense? So that means we can cancel. Obviously this is not the right free body diagram because they haven't removed the supports. The very definition of free body diagram tells you that you need to remove all the supports, you need to isolate the body, then show the different external forces that are acting on the system. So obviously this is not the right answer. Now coming to B, we don't know whether it is the right or wrong answer, so just hold it there. Then C, here they have shown both normal force and the frictional force. Since they are asking us the free body diagram when it is just about to climb over the step, this is also wrong. Why this is wrong? Because when it is just about to climb, these two forces would not be there. So we have removed, or we have successfully eliminated two options. We are left with only two options, this one and this one. See, if you fall to the trap created by the person who created this question, then you would pick this option, option D. Why? Because they're clearly telling you there is friction here. They're clearly telling you the coefficient of friction at this location is mu. So that means there will be a normal force from this point. I'm showing you this is the normal force from this point. So there will be a normal force from this point, like this, capital N2. Then correspondingly there will be a frictional force also, mu N2. But this is wrong answer. This one is a wrong answer. even though it agrees with all the assumptions that we have made, this is the wrong answer and this is the right answer, because we are only left with this option. Why this is wrong? Pause the video, think on your own why this is the wrong answer, and then come back. See, the reason is pretty simple. We are talking about equilibrium diagrams or free body diagrams. In essence, this diagram corresponds to the state where the whole system is in a state of equilibrium. See, you can see over here all the three forces passes through the same point. Triangle law, you remember in mechanics, when you have three forces that form a triangle, it is the sum of the forces will be zero. There is another reason why this is wrong. Why this is wrong is, if you take the moments about this point, if you sum up, if let's say this point is O and I want to sum up the moments about O, then I have mu n2 times the radius. But since this is a free body diagram that corresponds to a system in equilibrium, I cannot have a non-zero moment about this point. If I sum up the moments about this point, I should get zero. I should get zero only in this case. If I have a zero, I won't get zero moments about this point or for corresponding to this case, which in turn means that mu n2 is zero. So the correct answer is this. Beautiful problem. So I will tell you two concepts. Concept number one, when it is just about to lift off, there won't be any contact at this point, which in turn means that there won't be any external forces acting on the roller from this point. This W is acting through this, it is not from this contact, so there won't be any contact forces at this moment. These two figures, both options, these two B and D, were agreeing to that because they didn't have any frictional forces or normal forces acting at this point. So these two agreed to that. But we are talking about equilibrium diagrams, so once you take moments about any point on the system, you should get zero. But in this case, we won't get zero, we get mu n2 times capital R, which in turn means that mu n2 is zero, or this is the correct free body diagram of the system. A beautiful problem. This is taken from the Engineering Mechanics and Dynamics book of S.P. Timoshenko. It's a very good book. It's a very short book. If you're really serious about learning mechanics and dynamics, I will seriously recommend that book. It's from the Timoshenko's. It's written by Timoshenko. He's a very famous professor in mechanics. I think he was in Stanford. So thanks for watching. We did two really beautiful problems which will really test a candidate's understanding in basic mechanical engineering concepts. Thanks for watching.